P1 here, you can think of it this way. I just draw the block for you only. So you go and get one AND gate, another AND gate, one AND gate to generate this one, another AND gate to generate the second one. Okay, so all in, I need 4. 1, 2, 3, 4, because got 4 prime impedance. So each one of them, okay, 3 input variables. Okay, after this, okay, you find that all these output from the first level NAND gates here, you are going to make it become the input to the second level. Okay, and you are going to get your P1 from here. So this is the structure of your P1 using NAND gates. Okay to all? Okay, so we will look at, okay, now the second part here using NOR gate. So answer is here already, double confirm. So NOR gate, like I say, okay, I am not going to draw another Carnot map because the same Carnot map can be used to get my NOR gates here. And for the case of NOR gate, actually, okay, I'm trying to get maximum. For maximum, okay, I can get my NOR gate implementation. Okay, this is the answer. All right. So now, so just now using the red color, now let's say I use a blue color for my looping. Okay, blue color for looping for the P2, for example. I am going to loop these 8 together. Next, I loop another 8 together. This single one here forms a looping of 4. So now my P1 for looping of this 0 here, let's look at this horizontal square here. You are going to find that it is given as B1. Okay, these loops here give me B1. Why B1? Because all are changing. So the A, you can forget about it. This one here, B0 is changing, forget about it. Maximum, because you are looping 0. So the B1 is a 0. So 0, you write the time as no bar, maximum. Next, this part, vertical, okay, this vertical loop. What you have here is you see a A0 bar. So you write here as A1 bar. You see right here as A1. Next, this one. This one here, you see A0 is a 1, isn't it? So you write as A0 bar. I make a mistake. So it's a dot. Wait, it's a dot. Cannot synchronize already, okay? It's a dot. Okay. So it's a dot. Okay. Next, this square here. A0, you see a 1, so you write as A bar, A0 bar. This one, you see B0 is a 1, right? So you write as a B0, 1, correct? B0 bar. And this is for these loops here, so sum term, sum. Okay, so this is the P1. Okay, P1, P2 lah. Okay, P2 for this one. And for the case of P1, this looping. Okay, so we write here, P1. This loopings here, you see B1, B0. So B1, B0. Both are 0, 0. So you write as no bar. Then you all them. Okay, one sum term. Next. So I go for the larger one first. So this part here is your A1, A0. All right, you all them. This one. Then next, we have this one here, 4 of them. which in this case here is given as A1. Okay, this one here is the B1. You all them. Okay, one more. This is a 0. Don't just loop this one. Remember, we can do this looping, right? Okay, this looping here is the same as your, wait, this is the A0. Okay, A0. Okay, A0. And this part here is the B0. Okay, last, this one. This is one by itself. And this one by itself is going to give you the A1 bar plus A0 bar plus B1 bar plus B0 bar. Okay. This one, the looping is 4, 4. Sorry, it's not 4. So do it as a 8. Okay, one of them. So P0. This one here is the same as my A0. A0, that's all. Yeah, A0. Then next, okay, this one. Okay, is your B0. So you find that exactly the same. All right, exactly the same. You end, isn't it? So one term, you end with another term. All right. Now, for the case of P3 here, there are many, many zeros, only got single one. You can go and do all the looping, or you can play around with this. So you take a P3, same as this one, because you want the XOR expressions. All right, then you find that if you do the looping, okay, you are going to get the same answer for this one. Okay. Okay. Now these expressions, okay, I have already. Then now how am I going to implement them using NOR gate? So, well, this part quite easy. You are going to find that, okay, the structure, okay, look something like this. Of course, okay, you change this NAND gate here to NOR gate. Okay, change it to NOR gates. So 1, 2, 3, 4, 5. Okay, so you have your 5. Okay, after getting the 5, so I purposely draw 5 here. 1, 2, 3, 4, 5. Then you make it becomes an input to the second level NOR gate to get your P1 function. Okay, so here got 2 inputs. This one here got 4 inputs. And we don't need to generate the A0, A1, and so on because available. All right, so structure looks something like this. Then what about this one? This is the one that students always make mistake, P2. Cannot put on top already, P2. So I label P1. Okay, P2 here. You find that, okay, this one here, let's say, oh, how am I going to do it? Let's say, okay, for example, I follow exactly what I'm having over here. Of course, okay, first one, I put a NOR gate with the input here, follow A not bar, B not bar. All right, then let's say, okay, I take this one. Directly, because this is the features of no for one looping ma, okay, another looping ma. So let's say, okay, I put it this way. Okay, the B1 A1 B1 A1. I go to this second level NOR gates. Will I be getting P2 or not? We are going to confirm. Okay, so this one, of course, okay, we know that is a A0 bar NOR plus with the B0 bar I bar it. Okay, come to here. So if this is the input, so you are going to have a B1 plus A1 plus A1. Okay, B1 plus A1 plus with this one. Okay, then bar it. So when I bar it, I apply, after this, okay, I apply the Morgan's theorem. Then you are going to have this one here is a B1 bar. This is the A1 bar, the Morgan's theorem, okay? This bar here become dot. Okay, dot. This one here become dot. Double bar. Okay, compare this one with the original answer after the looping. You find that these two are wrong if you were to do it this way. So that to say, okay, I need to convert this one, okay, this B1 bar here back to B1. So indirectly, I'm trying to tell you here, okay, I need one B1, okay, B1. If I follow the question, I need this one. But you know that, okay, what you need here is the B1 bar as the input. You can directly connect this one to B1 bar or do it this way if you want it to be systematic. All right, so whatever term there, okay, although, okay, you see here as a B1, remember, you need a bar, you need to make it go through one inverter, okay, or NOR gate in this case, okay, make it go through one NOR gate, all right, this way. Or if you don't want to make it go through one NOR gate directly, okay, you must connect to the complements of it. That is the B1 bar. This one, same thing, okay? I make it connect to my A1 bar. Then I can get the answer that I want. So because the input now is the bar here, then I have a double bar. Then this solution is exactly the same as what we have for the answer. Clear to all? Okay, so this is a structures, okay, for your NAND gate and NOR gate. So for this one here, of course, okay, two level lah, this one, so you find that okay. So you are going to put in this one here as wait, oh, this one here I need more level. Oh, because I'm taking the P3 bar. Okay, so if I follow, okay, what I'm having over here, all right, So this is a P3, P3, I can have it as no, just you take this input as a A1 bar input, A0 bar, B1 bar, B0 bar. All right, so when you take this input in, you got a bar across them. Where is my, okay, then you can get your P3 as in this form. Is that okay? Okay to all? Okay, so you need to spend some time, okay? Go and practice all this. Okay, well, next, I choose question 4. Okay, question 5, think about it. Come up with a truth table, then you are going to do it on your own. Okay, our question 5. Read through. Let's see, okay, what do we understand? Ask me to design a combinational circuit with 3 data inputs, 2 control input. That means you got 5 variables. All right. And this circuit here, 2 output, R1, R0. The R1, R0 should be the quantum after dividing the unsigned binary numbers formed from D2, D1, D0 by the unsigned binary number formed by C1, C0. So indirectly whole thing, what I understand up to here is this one. So my D1, D2, D1, D0 will be divided by C1, C0. Okay, they are going to give me a result called R1, R0. So quantum. The quantum after dividing the this one by this one. Okay, for example, they say, for example, okay, if this one is 111, this 111 means actually 7, isn't it? C1, C2 is a 10 means it's 2, right? Then result for your this one should be P, should be R, isn't it? Okay, typo error, R1, R0. Okay. Okay, R1, R0. So it's a 7. Read it in a max way. It's a 7 divided by 2. Okay, it's going to give you a quantum of 3. Okay, 2 times 3 give you 6. Then you have a remainder of 1. Here, never ask me to go for any remainder. All right. Note division by 0. This one here never occur. You are not going to have a 0, 0 for these conditions. So with these conditions here, because never occur, please, okay, take it as don't care in this case. So present the truth table for this circuit. Okay, present the truth table for this circuit. So how am I going to have this? I got 5 input, but this one never occur. So after that, okay, with the Kano map here, ask you to derive this one using NAND gate. Then same thing, you can use the same Kano map for your NOR gates. Can I leave the this one for you all? This is a question that I found, okay, last short semester. So no answer yet, waiting for you all to give me the answer. Okay, so I explained to you how it functions already. So please, okay, give me the solution. Think about it, okay, how can you make it in a shorter way? And I will have two output, okay, the R1 output and the R0 output, two output. As you see from here, two outputs here. Okay. Yes, this question is a 5 input one. Okay, next. So I explained already, should be able to do it. Okay, this is a question number 5, no answer. Okay, so this question 1 to 5 here are mainly on your this you see I put here as a NAND gate and NOR gate implementations. Okay, so you design based on NAND gate NOR gate and so on. All right. Then next, okay, these parts here is on your multiplexers already. Okay, Kibun got one question. So if you divide 1 by 3, okay, let's see here. You divide, that means your D is a 0, 0, 1, isn't it? Okay. Your C is a 1, 1. All is 1 divided by 3. So can you tell me how you divide this one? What is the answer that you obtain here? Kibun? Am I right to say that my quadrium in this case here is equals to 0? Remainder is a 1. So I need only this one. Okay, decimal point to 1. Decimal point to 1. So anything less than 3 here, well, you're going to get a 0 as the output. Okay, so okay, recall, okay, multiplexer. An 8 to 1 multiplexer have input A, B, and C. 8 to 1, so 3 input connected in the, this questions here, I actually also, okay, I think put it into the year 1. Yes, very similar because you need these foundations here. All right, so some of the questions here are trying to help you to recall. Okay, so this one here, okay, so if you say you can remember, I skip this part. Please give me the solution. Please give me the solution. Okay. Yes, skip, but you all have to do. Okay, question number 4. Question number 4. Maybe I cut here. So So I add page, okay. So I'm going to put here as a marks, multiplexer, under multiplexer Q4. Okay, how to do this one? My this functions here, 4 input. All right. So if I use multiplexer with 16 input, very easy. All right. 8 input also not difficult. But question asks for 4 to 1 multiplexer. Use 4 to 1 multiplexer and external gates so that okay you can generate all these functions here, or these are functions expressions here. Okay, to make it easy, okay, I come up with the truth table here. So let me go and get the truth table. I think I put it here. Okay, it's here. Now I need only one output. Okay, so I cut here only. Okay. Mana you? I need to go to insert, is it? No. File? No. Home. Okay. Where is my arrow? Okay. Where's my question now? Okay, so I think okay, side by side we can see better. Cut the one. I want to close this one. All right. Now realize the following Boolean expressions. So my function is given as in this. All right, 4, 5, 7, 8, and this is a min term. So I can label accordingly. Follow okay whatever question given. So W X Y Z. Okay, W X Y Z. So this one here standard. And now output here label as F. So this is F. So with this, okay, 4, 5, 7, 8. Remember, minterm start 0, 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So whichever not mentioned, you either leave it blank or fill it in with 0. All right, so this is the Kano map question never asked me to do, but maybe it will help me, okay, to answer the question more easier. Okay, so now they say that, okay, I was given a 4 to 1 multiplexer and question decided for me. W and X will appear at the selector input. Okay, 4 to 1. Okay, I think enough space. So my selector input WX decided by the questions. So of course, okay, 4 inputs here. My I0, input 0, input 1, input 2, input 3, and I have only one output. This output, I want it to function, okay? Generate the function F over here. So now WX, I have to class them as one group. So in this case here, both are 0, 0, both are 0, 1, 1, 0, and 1, 1. So what we are going to see here, the difference is here only this part. Okay, this parts here. So this all 4 here, I'm going to put it here. I repeat, all these 4 here, I'm going to put it here. Of course, you can go through the method, okay, slowly do it. But if I were to see from this Kano maps here, these 4, I find that, okay, their output all are 0. So very conveniently, I'm going to say that, okay, this one here connect to a 0. Because when these are these two input here are 0, 0, they are going to choose this one as their output. And this output here is a 0. Okay, then the next combinations, this one, more complicated a bit, 1, 1, 0, 1. So what should I put here? Actually, okay, with this 1, 1, 0, 1 here, you are going to find that I can come up with a small, very small Kano map. If you can see from here, okay lah. If not, okay, I can come up with a very small Kano map containing, okay, the variables of Y and your Z. Y, Z. So, of course, this is 0, 1, this is 0, 1. So you find that, okay, I am going to fill in here 1, 1, 0, 1 into this small Kano map here, which is a Y, 1, 1, 0, 1. Okay, so this is for my I1. So I write down here I1. So of course you can do the looping. You find that this is a Y bar. This one here is the Z. So that is to say, over here, I will use one OR gate. Connect to Y bar, connect to Z. For the case of I2, okay, this is the I2. You also do the same thing. Okay, YZ. Okay, 1, 0, 1, 0. So 1, 0, 1, 0. And you find that, okay, this one here, you need to connect it to Z0 bar only from here that I see. Last one. Last one, a bit complex. Okay, this is I2. I2 is a Z only. Okay, so the case of I3 here, 1, 0, 0, 1. So 1, 0, 0, 1. So you know that you cannot, okay, loop them. And this I3 is actually given as, so if you were to work out, this is a Y0, this is a Z0 plus it with Y plus it with Z. And of course, this is the same as your X NOR gate. Okay, X NOR gate. So with this, okay, these parts here, X NOR gate. Okay, I can implement this function here using 4 to 1 decoder plus some external gate. Okay, so this is the first one. Second one, change, okay, my selected input here to Y and Z. Okay, so your these parts here will contain the variables of W and your X. So let you all try out. So this is an expression that I'm having. All right. Okay, so multiplexer is this one only. So this question number 3 also should try out. So this part here a bit typical lah. Then I can follow with adder. So expect you to know the truth table internal architecture. Don't go and remember the internal architecture. We only remember the truth table. From the truth table, we get our circuit. Okay, so try number 2 especially. Number 3. Okay, so you see, now instead of using gates to implement the full adder, I may want to use multiplexer combine. Okay, then making use of this full adder using decoder. We already covered decoder and all gates. So please try your adder as well. Okay, so hopefully can try until this decoder. Adder, sorry, adder. So we keep this one here because this one combined with encoder. Okay, so will I be able to see some solutions? Now I have to finish this tutorial, then only we will having our test. So this is week 7. Can we have our test on week 9? Can we have our test on week 9? Okay, week 9, Monday. 7, 9. Okay, 9, Monday. So week 9, Monday. So please do your tutorial. Saturday, Sunday can study. Okay. No need to study, you practice only. So remember 5 variables sure come out. So today is 14 days later. So this is week 7. So 2 more weeks later, week 9. So by week 8, we have to finish all the tutorial here. Right. So I guess we have to stop here. So this Thursday, anyway, this Thursday I will finish my lecture on encoder first. Then we focus on tutorial and try to finish all our tutorial before the end of this week 8 so that you have enough time to go for your revision. Okay, so we stop here for today. So take care. Bye-bye.